In this video, we'll talk through the notes for section 4.3, Generalization and Singular Problems, for the Sturm-Liouville problem. A weighted Sturm-Liouville problem has the form that you see here. This Sturm-Liouville problem looks just like the regular Sturm-Liouville problem, except we have an additional function involved. So on the left it's the same. We have the opposite of the derivative of the product of p times y prime, plus q times y. But on the right, we have that that's equal to lambda times a function r at x times y. Our boundary conditions are the same. We have them written in this mixed way. Alpha 1 times y at a plus alpha 2 times y prime at a equals 0, and beta 1 times y at b plus beta 2 times y prime at b equals 0. Again, this is for x between a and b, so our boundaries are at x equals a and x equals b. As before, we're going to assume that p, p prime, and q are continuous on this interval, and that p at x is not equal to 0 for any of the x's in the interval from a to b. And we also want to assume that it's not the case that both alphas are 0 and both betas are 0. That is to say, we assume alpha 1 squared plus alpha 2 squared is not 0, so it's not true that both alphas are 0. And beta 1 squared plus beta 2 squared is not 0, so that both betas are not 0. But we now also have this function r. So r is going to be a positive continuous function, and we call it the weight function. The Sturm-Liouville theorem is still true, but we must replace our inner product with what we call a weighted inner product, which we still denote the same way, except we put a little w there to indicate that it's weighted at the bottom right as a subscript to our inner product notation. So it's defined to be the weak inner product, so you just use the regular inner product notation for these two functions, y1 and y2, but you just have that little subscript w to indicate that it's weighted. So so if we look at the weighted inner product of y1 with y2, that's the integral from a to b of y1 times y2 times r, integrated with respect to x. So this is the weighted inner product, and it leads to a weighted norm. The weighted norm is denoted in the same way as the L2 norm, except we just replace the L2 with a w. But otherwise it's the same. So the weighted norm of y is the square root of the weighted inner product of y with itself. So theorem, and this is really just the Sturm-Liouville theorem with the inner product replaced with the weighted inner product. So for a weighted SLP on an interval, closed interval AB, there are infinitely many distinct eigenvalues, lambda sub n, which form a sequence, each of which is real, and the limit as n goes to infinity of the absolute value of these lambda n's is infinite. Furthermore, each lambda n corresponds to exactly one eigenfunction, up to a constant multiple. And the set yn of eigenfunctions is a complete orthogonal system with respect to the weighted inner product, which is the inner product with the w subscript. What does that mean? That means that if you have two eigenfunctions, ym and yn, and you compute their weighted inner product, that's equal to the integral from a to b of ym times yn times r dx. And this is equal to 0 if m is not equal to n, and it's non-zero if m is equal to n. In this case, it would equal the weighted norm of yn squared if m was equal to n. And furthermore, if f is a function that has weighted L2 norm which is finite, that is, so this is the square of the weighted L2 norm. So we're looking at the weighted norm, which is the integral of f at x quantity squared, but we're integrating with respect to r times dx. So that's remember the weighted L2 norm, or the weighted norm, is equal to the inner product, the weighted inner product of the function with itself. So that's what we have here. So if we just go back to the definition of the weighted norm, here it's the square root of the inner product of the function with itself. So here we're just looking at f instead of y. So the weighted inner product of f with itself is the integral of f times f times r dx. And we've squared this, so this is the square of the weighted norm. I'm calling it the weighted L2 norm as well because that's what it is. It's an L2 norm, but it's weighted. So we even use this notation L2 with a subscript W to indicate the weighted L2 norm. So if f has weighted norm squared, which is finite, then f can be written as a Fourier series in terms of these eigenfunctions. So f at x is equal to the infinite sum, n equals 1 to infinity, of Cn times Yn of x. And this convergence is in the weak L2 norm sense, where these Cn's are the Fourier coefficients. So those are computed in the same way. We're just looking at the weighted inner product now. So it's the inner product of, or the weighted inner product of f with yn divided by the norm, the weighted norm of yn squared, which is just equal to the integral of f times yn times r divided by the weighted norm of yn squared. This is just for normalization. And that gives you your Fourier coefficient. So we have the same theorem here, it's just now we have the addition of all of these little weight functions r. So let's look at an example. Consider the boundary value problem you see here. Minus y double prime plus y prime equals lambda y, where x is between 0 and 1. And we have these boundary conditions. Y at 0 is 0 and y at 1 is 0. This problem looks a lot like a Sturm-Liouville problem, but it isn't in the right form. Notice that there's a y prime here. However, if you multiply by an integrating factor, you can put it in the right form, except that it will now be weighted. So if you multiply by the integrating factor e to the minus x, then the differential equation takes on this form. So I just have the same differential equation here. I've just multiplied everything by e to the negative x. But the reason that we do that is we can recognize that the term on the left is now the result of a product rule. So this is very similar to solving differential equations that are ordinary differential equations using an integrating factor. We just multiply it by the necessary thing to make the term on the left look like the derivative of a product. And we can do that here. And that puts us in the correct form. Now this isn't a regular Sturm-Liouville problem, but it's a weighted one. It's a weighted one with the weight e to the negative x. So this has the correct form with p at x equals e to the negative x and q at x equals 0. Now in this case all of the eigenvalues are positive, and we'll show that later using an energy argument. So we can actually solve the original differential equation since it is a linear second order ODE with constant coefficients, and it's a fairly straightforward computation. What I do want to comment on before we do that, however, is that this method works in general. If you have a y prime in your differential equation, you can multiply by some integrating factor to get it in the right form to become a Sturm-Liouville problem, at least with a weight. This is something that can often be done when you have a differential equation that isn't in the right form. Okay, so let's go back to our problem here. We want to solve the original differential equation, which is minus y double prime plus y prime equals lambda y. Now we know that this boundary value problem does have a solution because we can rewrite it as a weighted Sturm-Liouville problem, and then our theory tells us that there are solutions. And in fact we know that there are countably many eigenvalues that each correspond to a unique eigenfunction. So we know that there are solutions, and as I said before, we can show that all of the eigenvalues are positive. So we know that lambda is positive. So we write our differential equation in the following form: y double prime minus y prime plus lambda y equals 0. So this has characteristic equation s squared minus s plus lambda equals 0. So we can find solutions to the characteristic equation using the quadratic formula, and we get that s is equal to 1/2 plus or minus the square root of 1/4 minus lambda. Now the nature of the solution will then depend on whether or not this quantity is positive or negative. And when I say this quantity, I mean the thing underneath the radical, or possibly 0. So we can check these situations. So if lambda is actually equal to 1/4, well, let me just leave a little bit of the problem on the screen here. So if lambda is equal to 1/4, then the radical goes away. It's 1/4 minus 1/4 is 0. So that means you have a double root of 1/2 for your characteristic equation. So if lambda is equal to 1/4, then the general solution is y equals a times e to the x over 2, because s is equal to 1/2, plus b times x times e to the x over 2. Again, because s is a double root. So it's e. So the first of your, what you might call your fundamental solutions, is e to the x over 2, and the second one is x times e to the x over 2. So then we try our boundary conditions. Y at 0 gives you a, because if x is equal to 0, this term goes away, and e to the 0 is 0, so you just end up with a. So y at 0 is equal to a, but this is a homogeneous boundary condition, so it's equal to 0, and that tells us that a is equal to 0. So this term goes away. Now y at 1 is a times e to the 1/2 plus b times e to the 1/2, but we know that a is equal to 0. So that tells us that this term goes away, and we're just looking at b times the square root of e is equal to 0. So that tells us that b is equal to 0. So that means we only have the trivial solution. So only solution is the trivial one, y equals 0, which is not what we consider an eigenfunction. So what about the case where lambda is less than 1/4? In that case, the thing underneath the radical is positive. So you have two distinct real solutions, so you'll have exponentials. So you can see those here. So your solution, your general solution, is y equals a times the first exponential plus b times the second exponential. So I've written the exponent, or the exponential here, as e to the 1/2 plus mu times x, and e to the 1/2 minus mu times x. So mu is just shorthand for this radical term. So mu is 1/4 minus lambda. So that's really hard to read for some reason. So let me just make it a little bit bigger. 1/4 minus lambda. And we're looking at the positive square root, which is why I had that written as greater than 0. So it's 1/2 plus or minus mu. So I'm calling this thing in a circle that I've circled, I'm calling that mu. So the solutions are 1/2 plus or minus mu. So those are what you see showing up in the exponent here. So we have two real zeros, so that gives us exponential solutions. Now our boundary conditions in this case will also tell us that we have a trivial solution. So y at 0 is just going to be a plus b, which is equal to 0, because our boundary condition is homogeneous. Y at 0 is equal to 0. So that tells us that a plus b is equal to 0, so b is equal to the opposite of a. So then we can just plug that into y of 1. So y of 1 is what you get when x is equal to 1. So that gives us a times e to the 1/2 plus u plus b times e to the 1/2 minus mu. And that's equal to 0 as well. Now we know that b is equal to the opposite of a, so we just substitute in right here the opposite of a, and then I factored it out right there. So this a is what happens when you factor out that a, and you're just left with a difference of these two exponentials. So we can factor out the e to the 1/2 as well, so that e to the 1/2 is that e to the 1/2, and that just leaves behind first an e to the mu and then an e to the minus mu, and we're looking at their difference because it's minus a here. B is equal to the opposite of a, so that introduces a minus sign, which is that minus sign. So this is 2 times the hyperbolic sign of mu. Now, in order for this expression to be equal to 0, one of these factors has to be 0. The square root of e can't be 0. This term can't be 0. The difference of these exponentials, this hyperbolic sign of mu, that can't be 0 unless mu is 0, and it's not. So we're assuming that lambda is less than 1/4. So mu is not 0 in particular. So this thing right here cannot be 0. So that means the only option is that a is equal to 0. And so we get a is 0 and b is the opposite of a, so b is 0. So that means that y is 0, is the only solution. Okay, so that means our only possibility is that lambda is actually greater than 1/4. If lambda is greater than 1/4, then this mu term is purely imaginary, because if lambda is greater than 1/4, then underneath the radical is a negative term. So that means mu is imaginary. So that way we can write s is equal to 1/2 plus or minus an imaginary number. So let's do that here in this way. So s is equal to 1/2 plus or minus the square root of 1/4 minus lambda. But if, again, lambda is greater than 1/4. So we can write that as lambda minus 1/4 if we introduce a minus sign. And so the square root of that minus sign gives us the I. So we've written this as 1/2 plus or minus I times the square root of lambda minus 1/4. And since lambda is greater than 1/4, this quantity lambda minus 1/4 is greater than 0. Okay, so we've written s as a complex number, and in fact it's two complex conjugates, so that gives us a solution in terms of sines and cosines. Of course, the real part is non-zero, so that gives us an exponential. So what do we end up with our general solution? We have y is equal to a times e to the 1/2 x, so that's the real part, times x, times cosine of x times the imaginary part, plus b times e to the x over 2, and again it's x times the real part, which is 1/2, times sine of x times the imaginary part. So this is our general solution. We can check our initial conditions, or not our initial conditions, in this case they're boundary conditions, which are homogeneous. So y at 0, if x is equal to 0, then this sine term goes away. Sine of 0 is 0. So this term disappears. And then we have y is equal to a times e, so we're looking at x equals 0 here. So y at 0 is a times e to the 0 over 2 times cosine of 0 times all that stuff. I'll just leave it that way. But of course that's just a. And this term, remember, goes away because sine of 0 is 0. Now our boundary condition is that y of 0 is equal to 0. So that tells us right away that a is equal to 0. So in fact, this term isn't there. So if we want to compute y at 1, we just need to look at this part because the a is equal to 0. So y at 1 is b times e to the 1/2, which is non-zero, times sine of 1 times the square root of lambda minus 1/4. Now sine, well, since this b times e to the 1/2 can't be 0, and we know that our boundary condition y at 1 has to be 0, our boundary value has to be 0, then we know that sine of this object must be 0. So that means the thing inside the thing inside is the square root of lambda minus 1/4. So we know that sine of that object is 0, so that means the thing inside the sine must be n times pi for some integer n. Now we're assuming that lambda is greater than 1/4, so in particular it's positive. So that means we're going to say that the square root of lambda minus 1/4 is n times pi, where n is a positive integer. So n is in the natural numbers. So square both sides. Lambda minus 1/4 is equal to the product n times pi quantity squared. And so you just add 1/4. Lambda equals 1/4 plus n squared times pi squared. So our eigenvalue eigenfunction pairs are lambda n equals 1/4 plus n squared pi squared, and our eigenfunction is yn, and our yn, we just come back up to our solution. Remember, the a was equal to 0, so this term went away. So we want some function that represents this family, so we can ignore the b, and we just have e to the x over 2 times sine of x times the square root of lambda minus 1/4. But remember what lambda is. Lambda is 1/4 plus n squared times pi squared. So the 1/4s cancel, and you're just left with the square root of n squared pi squared. So it's just n pi times x. So let me just say that if lambda is equal to 1/4 plus n squared pi squared, then the square root of lambda minus 1/4 is the square root of n squared times pi squared, which is just n pi. And that's what's right here. And this gives us our eigenvalue-eigenfunction pairs, and we have one of these for each n in the set of natural numbers. So note that the eigenfunctions are orthogonal, but with respect to the weight e to the minus x. That was the weight way back at the start of the problem. That was our weight function, e to the negative x. So we can show that these eigenfunctions are orthogonal with respect to that weight. If we compute their weighted inner product, that's going to be the integral with respect to that weight. So if you take a ym and yn, where m is not equal to n, and you look at their weighted inner product, that's the integral of ym, which is this first one right here. This is ym times yn times the weight, which is e to the negative x. So you have this e to the x over 2 and this e to the x over 2. You combine those to get e to the x, and then you multiply that by e to the negative x and you get 1. So these terms combine to give you 1. So you just end up with the integral from 0 to 1 of sine of n pi x times sine of m pi x dx, which we know is equal to 0 if n is not equal to m. So we see that these eigenfunctions are indeed orthogonal with respect to the weight. So let's make a remark here. The Rayleigh quotient for the weighted SLP takes the same form as the regular SLP. It's just now you have to change the L2 norm with the weighted norm. And so you end up with exactly the same formula, just now you have the weighted norm here. Now, why is this true? It really works the same way. The argument works the same way. So if you start with the differential equation that you see here, so this is the weighted differential equation. Notice I've suppressed all of the arguments, but all of these are functions of x. So we have our differential equation here, which is our weighted equation. There's a little r there. Now, the thing on the left is exactly the same as it is in a regular Sturm-Liouville problem. The only change is that you have your weight on the right. So we proceed as we did before, so you integrate both sides. Now on the left you have exactly the same term. So you can argue just as you did before, and you use integration by parts, and then combine terms. On the right, instead of having lambda times the integral of y squared, you have lambda times the integral of y squared times r. And I forgot to mention that you multiply by y, but you multiply the differential equation by y first, and then you integrate both sides, and then you have the same thing that you had on the left before. So on the right, you have lambda times the integral of y squared times r. So before, you ended up with the L2 norm of y squared, and here you just have the weighted norm of y squared. But otherwise, everything is the same. So on the left, you use integration by parts, combine terms, look at the boundary, etc., and then you just divide instead of dividing by the L2 norm squared, you divide by the weighted norm squared, but it's exactly the same. So you end up with the same formula, just you end up with a W there instead of an L2. So in our example, we have this differential equation. This is the one that's been rewritten so it looks like a weighted Sturm-Liouville equation. So here our P is e to the negative x, and our weight is also e to the negative x, and q is equal to 0. So if you take lambda, and if you just look at this formula here, and just replace all of the relevant parts, so p becomes e to the negative x, this p becomes e to the negative x, this q becomes 0. So what happens? Well, on this part which is circled, I have it marked as going to 0. That's because at the boundary, we know that y at 1 and y at 0 are both 0. So this whole term goes away. This term goes away as well because q is equal to 0. So you just end up with the integral from 0 to 1 of e to the negative x times y prime of x quantity squared, divided by the I keep calling it the weak, but it's the weighted norm squared. This quantity is certainly non-negative because everything is positive that's involved here. So that tells us that lambda is non-negative, but the only way it could be equal to 0 is if the numerator was 0, and that could only happen if y prime was equal to 0 for all x, which means that y is constant. But the boundary conditions would then tell us that y must be 0, and that's a trivial solution, so we don't want y equals 0. So that tells us that lambda is positive. So we now know that lambda is positive. What is not obvious, at least it's not obvious to me, is that this quantity is actually greater than 1/4. And since it wasn't obvious that this quantity was greater than 1/4, we still had to consider the different cases. So it's not really necessarily true that this was helpful to us for this particular example, but there are certainly cases where this would be helpful because it would eliminate the need to consider separate cases. So we've been talking about a generalization of the Sturm-Liouville problem by adding a weight function. So another way that you can make it more general is by making what you call a singular problem. So let's look at the differential equation again. So this is the weighted Sturm-Liouville differential equation. You get a singular problem when this p is sometimes equal to 0. So if p at x is equal to 0 for some x in AB, you get a singular problem. Another way that can happen is if you replace this closed finite interval with an interval of infinite length. That will also give you a singular problem. We'll just look at one example of each of these. So the first example we'll look at is when you have a 0 for your function p. So consider the singular SL problem, Sturm-Liouville problem that you see here. So now we have that the opposite of the derivative of the product of x times y prime is equal to lambda xy. So our weight here is x. Our p at x is also x. So this is our p right there. And this is 0 at one of the endpoints. So this Sturm-Liouville problem is singular because p at x equals x, which is 0 at an endpoint. So this differential equation is called Bessel's equation, and it plays an important role in the solution of the initial boundary value problems for the heat equation on a disk of radius r, and we'll see that explicitly later. The SL operator that this defines, L at y is equal to the opposite of the derivative of xy prime, is self-adjoint. And so the SL theorem still applies in this case. So there is a countably infinite sequence of eigenvalues lambda n with corresponding eigenfunctions that are orthogonal with respect to the weight function Rx equals x. So the theorem still gives you a lot of information here. So we know that there are solutions. There are an infinite number of eigenvalues that form a sequence, and they each correspond to different eigenfunctions which are orthogonal with respect to our weight function. So our weight function is r, as you can see there. That's r. So this one is r of x, is this x right there. And this x is p at x right there. Now, we'll talk more about Bessel's equation in one of the later sections when we talk about diffusion on a disk. So here we're just noting the fact that the Sturm-Liouville theorem still applies in this case, even though we have a singular problem. Now here, we were looking at a problem, so to speak, at 0, which was one of the endpoints. That's where our function p became 0 at an endpoint. So how does that affect the boundary values? Well, since our problem becomes singular at x equals 0, we don't specify what y is actually equal to at 0 because we're not including that endpoint. So instead, you say that your solution y is, say, 0 at one endpoint, but at the other endpoint, you just assume something else. Usually you assume that it's bounded. So you want y to be bounded near x equals 0, rather than taking on a specific value. This is an example of a singular problem where the singular point happens at an endpoint. You can also have these singular points occurring inside the interval, but that's a little too advanced for something that we'll discuss in this course. So we want to look at another example, but this time you're looking at a case where it's singular because the interval is infinite. So let's look at a differential equation that we've spent plenty of time looking at, which is this one here. So minus y double prime equals lambda y, where x is greater than 0. So now we're assuming that this is an unbounded interval. X is positive, but growing without bound. So now we can say what a boundary value is at one endpoint because we have one boundary. So at 0, we can say that y of 0 is 0. But there is no other boundary, so we can't put in a boundary condition other than something asymptotic. So what we'll say is that y doesn't take on a value at infinity, of course. We'll just say that y is bounded. That's a traditional condition to impose on a singular problem. Just make sure that your solution is bounded at the point of singularity, so to speak, whether that means that your function p is equal to 0 at some point in the interval like it was here at the endpoint. Or here we're thinking about this as stretching our interval so it becomes infinitely long. So we have to have some asymptotic condition, so we say that y is bounded. So as I mentioned, this problem is singular because the interval is infinite. If lambda is equal to 0 or lambda is negative, then the solution is linear or exponential, respectively, which violates the boundedness assumption. So it must be true that lambda is positive. As usual, the general solution is given as you see here. Y equals a times cosine of x times the square root of lambda plus b times sine of x times the square root of lambda. So this is the general solution. The boundary condition y at 0 equals 0 tells us that a is equal to 0 in the way that it usually does. So we have that y at x is equal to b times sine of x times the square root of lambda. We don't have another boundary condition. All we know is that the function is bounded, but this is a sine of x times the square root of lambda, so this is bounded for every lambda greater than 0. And so we have a solution for each lambda greater than 0. Therefore, there are a continuum of eigenvalues. It's no longer a sequence, it's a continuum. The corresponding eigenfunctions are these sine terms. So for each lambda, we have a y sub lambda, which is sine of x times the square root of lambda. In this case, we don't have a system of mutually orthogonal eigenfunctions, so we don't get a Fourier series expansion, but there is a continuous version of the Fourier expansion. If f is piecewise continuous on the interval from 0 to infinity, and if it's what we call absolutely integrable, that is, if you can compute the integral from 0 to infinity of the absolute value of f. So if this integral converges to a finite number, then we say that f is absolutely integrable. So if f is piecewise continuous on the interval from 0 to infinity and absolutely integrable on this interval, then f at x is equal to 2 over pi times the integral from 0 to infinity of capital F at alpha times sine of alpha x d alpha, where lambda is equal to alpha squared, and capital F at alpha is what we call the Fourier sine transform. So f at alpha is the integral from 0 to infinity of f at x times sine of alpha x dx. So this is the continuous analog of the Fourier series expansion. So this is like a Fourier sine expansion, except it's continuous. It's an integral instead of a sum. These are some ways that you can generalize the regular Sturm-Liouville problem. You can either introduce a weight function, or you can talk about singular problems. And you can see that sometimes you get very similar results, but sometimes your results are quite different. Like in this last example, there are certainly similarities, but this is a very different outcome.